So if we could just open prayer real fast, or appropriately. Dear Lord, thank you for bringing us all together. Thank you for the really nice couple of days we've had, and thank you for the clear weather tonight so everybody can get here safely. Please bless our time together. Please bless this presentation and help me to pronounce words correctly. Please help us to have a great evening and everyone to get home safely. In Jesus' name we pray, amen. All right. Well, thank you all for coming back. I'm sorry that for those of you that I missed when I was out of town, and I'm sorry for those who couldn't make it last week. Nick is recording these for me, so if we get it all put together, I'm hoping to have that there. Pastor Cleve mentioned asking me to do one more week. I don't know if I can, but I might be able to redo the week that everybody missed with the snow. So let's kind of let's go back over where we've come. At this point, we're about halfway through. We're actually a little more halfway through this course. We've covered the fundamentals of evolution and all of its numerous flaws and problems. That was kind of the first two sessions. We spent the last couple of weeks discussing the Big Bang Theory as well as the age of the Earth and the age of the universe. And we talked last week very specifically about the many flaws of uniformitarianism thinking, which is, quote, the present is key to the past. So the rate at which we see things occurring now is the rate that it's always been. And this is very secular thinking. And we actually used that thinking to talk about why that sort of thinking actually points to a younger universe. In brief, for those who wisely avoided the ice last week, geologists have posited that the rock layers, that coal, that a lot of these things that we see, oil, took millions of years to form. But we actually showed last week numerous examples of rapid rock formation, examples of rapid coal formation. And what we discussed is that rock and coal formation is really a matter of conditions. It's not so much a matter of time, it's the right conditions. And under the right conditions, these things can form very quickly. We actually discussed that geologists tell us canyons, like the Grand Canyon, recur very slowly over millions of years as rivers like the Colorado River slowly eat away at these canyons. But we showed actually a couple of examples of canyons being formed in hours to days. And we looked at layers of rock, which are actually bent to 90-degree angles, and discussed that this could only have happened if those rock layers were laid down very quickly and in wet form. Think of concrete. You can mold wet concrete. You cannot mold hardened concrete. And then we looked at uniformitarianism models in geology, and we showed that they argue strongly for an Earth much younger than that posited by scientists. So I got my new handy dandy. And thanks to Dave for letting me borrow his for so long. And thanks to other Dave, who's black, who helps me set up every night. I think he stepped out for a sec. We also then turned to astronomical principles, or astronomy, and discussed how things like the rate of decay of the Earth's magnetic field, the recession of the moon, in other words, how the moon moves away from the Earth at a certain speed every year, and the existence of comets, which should be long gone if the universe was billions of years old. And we showed how these things show that the Earth cannot be as old as what secularists tell us. And finally, we discussed human history, and how interestingly all of human history seems to fit neatly into the last 5,000 years or so. Yet secularists tell us that modern man has been around for 200,000 to 300,000 years, which always leads me to ask, what were they doing for 245,000 years? So, in that light of that, we discussed where are all their bones from those 200,000 to 300,000 years of modern man. So, I think we did if I do say so myself, a fairly effective job of at least questioning the idea of the Earth and the universe being millions or billions years old. So tonight I want to turn to what the secularist strongest argument is for an old universe, which is radioisotope dating. Looking at the goals for the course in general, this is where we are. We're at about the halfway point here in red. So tonight we're going to talk very specifically about radioisotope dating, its potential flaws, and its potential uses in discussing the age of the Earth. Next week we'll talk about paleontology and start the journey onto Noah's flood, and that will be a couple weeks of discussing that. So, before you see the thing that says nuclear physics, As I have mentioned many times, this is my most complex topic. So, and I am not a nuclear physicist, and I actually had to read quite a bit to prepare this talk. So don't hit me too hard on the questions. But also bear with me. I know it is a little technical. My next few talks are not nearly as technical, but I think this is a very important topic to at least discuss, because this is the topic you are going to hear from secularists and specifically scientists over and over and over, that we know the Earth is a certain age based on radioisotope dating. So bear with me through the technicalities. I'll try to simplify it as best as I can. So on that note, nuclear physics, just ABCs. Going back, as we've talked about before, all matter is anything that exists basically, is composed of atoms. Atoms are made up of three things: protons, neutrons, electrons. Protons and neutrons exist in the nucleus, in the center of the atom. Protons carry a positive charge, neutrons carry a neutral charge. These two components are about the same size and sit in the center of the atom and are the nucleus. The electrons are very tiny negatively charged particles which are rapidly floating around the nucleus. That is what an atom is. If you recall, we talked in the past about how these size differences work. If the nucleus, which is composed of protons and neutrons, were the size of a tennis ball, the radius at which electrons are going around that nucleus are the size of Memorial Stadium. So keep in mind the protons and neutrons, even though that's the most of the weight of the atom itself, it's all very, very compressed and very tiny in the center, and you've got this huge area of air with these tiny electrons floating around it. Now, the number of protons in an atom is called its atomic number and determines what actual element we're talking about. So the lightest element on Earth is hydrogen. It contains exactly 1 proton. The next lightest element is helium. It contains 2 protons. Then lithium, I believe, is 3 protons. And that's how we get what the actual atom is. Now, when we start adding in neutrons, we get protons plus neutrons equals the atomic mass, as opposed to the atomic number, of that element. And different elements can have different composition of neutrons and thus different atomic masses. In other words, for hydrogen, it's always the same. It's 1 proton, 1 electron. But when you get into really heavy elements that have, say, 15 protons, they can have 15 neutrons, 16 neutrons, 17 neutrons. They're all the same element, but they have a different mass. And these various masses are called isotopes. So you get a nuclear isotope, which you may have heard, or radioisotope dating. What these are, isotopes are the same element. They're all carbon, for example, but they contain different number of neutrons, and you get different isotopes. Some of these isotopes are very stable and unchanging. They don't do anything except exist. Others are unstable, or the term is radioactive, meaning they will give off radiation and convert to another form. So, in picture form, this is your atom. This is your nucleus, protons and neutrons. These are the electrons rapidly flying around, okay? This is your tennis ball sitting in the middle of Memorial Stadium. These electrons are floating around Memorial Stadium in this way. This is everybody's favorite chart from high school, the periodic table that tells you what element we're looking at. So you start with 1 proton, hydrogen, 2 protons, helium, 3 protons, lithium, 4 protons, beryllium, I believe. And then we work our way across and we go to boron, carbon, nitrogen, oxygen, fluorine, neon. Aren't you impressed? I still remember all these. But this is how we get our name of our element is the number of neutrons. The name of the element is protons, excuse me. The name of the element is based on number of protons. The isotope is based on number of neutrons. I'm going to come back to that concept briefly, but that makes some sense? Sort of. All right. So, these radioactive elements, they can give off radiation in 3 different forms. So when we talk about radiation, when you hear about Madame Curie or other things that give off radiation, this is what we're talking about, is these radioactive elements giving off their radiation. And radiation can come in 3 forms: alpha, beta, gamma, for any of you who were, did Greek in college. So alpha particles are your largest type of radiation. These are 2 protons and 2 neutrons together that come flying out of the atom, and they radiate away. This is basically helium going away. Helium without the electrons being kicked out of the atom. So this can only happen from very heavy elements. For anybody who's seen Back to the Future, where they talked about polonium, this is one of those things. So uranium, polonium, and radium give off alpha particles. Alpha particles are very heavy. They cannot penetrate even your skin, but they are incredibly deadly if ingested. If any of you remember, about a decade ago, there was a Russian spy that showed up dead from drinking tea, and presumably what he drank was polonium that had alpha particles. So it didn't affect anybody who served him the tea because it couldn't get through the tea cup, but as soon as he drank it, it got into his intestines and destroyed him. So thanks, Putin. Beta particles, so those are alpha particles. Beta particles are a single electron. So an electron goes flying away from the atom. And this comes from lighter elements, things like carbon-14 that I'm sure you've heard of, strontium-90. The way they give off their radiation is from these beta particles. Now, these particles are much lighter than alpha particles, and they're therefore much faster than alpha particles. However, they're still not that strong. A single sheet of aluminum foil, or even the clothing on your skin, will stop a beta particle from getting into you. So far, we really haven't talked about any radiation that can hurt anybody. However, the gamma rays, which are extremely common, these are the things that we are often talking about when we're talking about radiation or effects of radiation on humans. This is a photon of energy. Photon is just a term that basically means it's sort of like light. It's energy. It has no mass. It is pure energy. Now, gamma rays are extremely penetrative. The only way you stop a gamma ray is multiple layers of lead or concrete to stop these. Side note, for those who are interested, X-rays like we use in medicine, they're actually very similar to gamma rays. As opposed to coming from the center of the nucleus for their energy, they come outside the nucleus and they're lower energy. Just a fun fact. So let's talk about decay rates and how this works. So these radioactive elements, they decay or turn into other isotopes at predictable rates. Now I'm going to introduce here a term called half-life that I suspect you've heard before, but the half-life is the amount of time it takes for 50% of your starting material to turn into your ending material, to get from point A to point B, for half of point A to turn into point B, is the half-life. You start with a parent radionuclide, and you end up with a daughter radionuclide. No sons, just daughters. So you get the parent and the daughter, and the amount of time it takes for the parent to be cut in half by their daughter is called the half-life. Every isotope has a different half-life. Some half-lives are fractions of a second, some are thousands, millions, some are actually even billions of years. It takes literally billions of years to turn this parent, 50% of this parent, into this daughter. So therefore, each half-life represents a 50% drop. So we start with 100% of A. We go through one half-life, we have 50%. We go through two half-lives, we have 25%. We get to 3, we're down to 12.5. We get to 4, we're down to 6.25, etc., etc. Does the concept of half-life make sense? Okay, so we're decaying a parent at a certain rate. Now, this is a chart showing the half-lives of various substances, some of which we will talk about tonight. The most common one, or the one we've heard the most about probably, is carbon-14. Carbon-14 decays into nitrogen-14 with a half-life of 5,730 years. I start with 100 units of carbon-14. After this amount of time, I have 50 units left. and I've developed 50 units of nitrogen-14. After 11,000 years, I now have 25 of these left, and I've got 75 of these. Make sense? Perfect. So this, just for interest, is how uranium eventually turns into lead. You'll see that the half-life of uranium-238 is 4.5 billion years. And then everything happens very quickly, actually. So thorium quickly turns into this one I'm not going to pronounce, which turns into uranium, thorium, radon, all the way down. But you can see there are multiple steps in each one of these. This is an alpha particle going off, a beta particle, alpha, 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 all the way down to lead-206, which is very stable. So how do we use this known half-life to actually date something? Well, because we know the half-times, or half-lives, or decay rates for certain elements, we can measure the amount of parents, we can measure the amount of daughters, and then derive an age for the material containing those isotopes. The way we do this is we assume that all daughter came from a parent. There was no daughter at the beginning, there was just parent, there was carbon-14, and then we now have nitrogen-14. We assume all nitrogen-14 came from the carbon-14. Now, these measurements can actually be made very precisely with a machine called a mass spectrometer, which is demonstrated here. So suffice it to say, I don't think one of the criticisms we can use about radioisotope dating is that they can't measure it. They can. Mass spectrometers are pretty accurate machines. So let me give you a simpler example that was in one of the books I read. You walk into a kitchen and you see me peeling potatoes, because it's what I do. After a while, you realize that I'm peeling them at about 5 a minute. And you see that I have 40 potatoes peeled. So I've got my peeled potatoes over here. Those are the daughter element. So you look and you assume that I've been peeling potatoes for 8 minutes. Because 8 minutes times 5 potatoes a minute is 40 potatoes. So you looked at my daughter potatoes, you said, you know what, he's cutting those 5 a minute, there's 40 of them there, that must have been 8 minutes. Okay, fair enough. Let's say you can't see those 40 potatoes, because they go on a conveyor belt somewhere. All you can see is the stack of potatoes I have left, the unpeeled potatoes. And you see an empty bag somewhere labeled 100 potatoes. And you see that I have 60 of those left. By the same math, I've still been at it for 5 minutes. You know I peel 5 every minute. You see the bag that said there were 100 to start, there's only 60 left. You know that I've been at it for 8 minutes. Make sense? Okay, same idea here. Now, let's talk about the assumptions in my potato peeling. So, is the rate you observe for my peeling, has it been the same the entire time? In other words, did I get better at it? Did I get speed up because I became more efficient, or did I slow down because I became more tired? Did I really start with 0 peeled potatoes, or did I come in and help my wife who peels them twice as fast as I do? The bag of 100 potatoes is the only source of unpeeled potatoes. You didn't see I had 2 bags underneath that were sitting there that were already empty. Or you're assuming that I didn't throw out a few bad potatoes, or my wife didn't come in and grab a few of the peeled potatoes that she already needed. All you can really verify, all you really know, is that I'm currently peeling potatoes at 5 per minute, and you can see the number of current peeled and unpeeled potatoes. That's all you know. So you've got a lot of assumptions on either side. Follow that? There's a lot of assumptions in this. So it makes sense when I first explain it, but then you start thinking about all the assumptions. Okay, so let's apply this then to radioisotope dating, and let's start with carbon-14 dating. The way carbon-14 dating works, carbon has 6 protons. Remember I told you the protons determine what element it is, what its atomic number is. So there are 6 protons every time in every form of carbon. But there are a varying number of neutrons, those neutral elements that make up the center of the atom. So carbon-12 is our most stable, most common form of carbon. It's what mostly exists out there. It is 6 protons and 6 neutrons. There's something called carbon-13, which is 6 protons, 7 neutrons. It also is stable, but it is not very common. And lastly, we have carbon-14, which is unstable. 6 protons, 8 neutrons. And this is how we label them in chemistry, by the way, as the number comes up here. So the element is C for carbon, and 14 tells us how many, its atomic mass, how many protons and neutrons. So you have to do a little in-your-head math, basically. You have to kind of know that carbon has 6 protons. Okay, I know that. 14 minus 6 is 8. That's how many neutrons it has. So don't worry about those details, but that's how they do that. Through beta decay, which you'll recall is shooting off an electron. So if you give up an electron, you throw away a negative charge. What that means is, by definition, one of those neutrons that was a neutral charge now became a proton. So you went from 0, you kicked out negativity and you gained positivity, if that makes sense. So you still have 14 items in your nucleus, but one of those neutrons became a proton. And the proton determines the element, so the element changes, and now you have nitrogen, which is 7 protons. So you took 6 protons and 8 neutrons, you turned 1 neutron into a proton, now you have 7 and 7, which by definition is nitrogen 14. Does that seem clear as mud? So we give off beta decay, we turn carbon-14 into nitrogen-14. The parent is carbon-14, the daughter is nitrogen-14. So, if carbon-14 is constantly converted to nitrogen-14, why don't we run out? Well, we actually don't, because nitrogen-14 is constantly being converted back to carbon-14. See, nitrogen's a gas, and when it gets exposed to cosmic rays, it bombards this and converts that proton back to a neutron. It kicks that electron back into there and says, nope, you're going to be carbon-14 again. So we're constantly regenerating the supply of carbon-14. Nitrogen's up in the atmosphere, cosmic rays bombard it, turn it into carbon-14. Carbon-14 then decays into nitrogen-14, which can then go back up and be bombarded. It's a continuous cycle. So carbon in all of its forms, whether it's carbon-12, 13, or 14, combines with oxygen to form CO2 or carbon dioxide, which I'm sure you've all heard of. Plants take this up. Animals eat plants. Therefore, all living things should contain carbon with a constant ratio of carbon-14 to carbon-12. Whatever's in the atmosphere, the plants absorb it, we eat the plants, we're all made of a constant ratio of carbon-14 to carbon-12. Whatever's in the atmosphere is what's in our body, it's what's in the plants. When a living thing dies, however, it stops taking in that carbon dioxide from the atmosphere or from the plants. We're no longer eating the plants. We're no longer consuming that constant ratio of carbon-14. Therefore, the carbon-14 that exists in us or the plants starts to decay into nitrogen, which again is a gas and will be given off without new carbon-14 to replace it. So you start losing your carbon. So when you die and you're decaying, as your body decays, the carbon that was part of you is given off into the atmosphere as nitrogen. So your ratio of carbon-14 and carbon-12 changes. You're losing carbon-14, but you're not losing carbon-12. So the ratio of 14 to 12 starts to change and decreases. You're getting less and less 14 with the same amount of 12. There will then be less carbon-14 to carbon-12, and eventually all that'll be left is carbon-12 and carbon-13, but that's not important for this. So if we know 3 pieces of information, we can therefore, using this principle, calculate how old an organism was when it died. What we need to know is the amount of carbon-14 in that organism now. That's easily measured. We put that organism into a mass spectrometer, we can measure that. We need to know the half-life of carbon-14. We happen to know that. It's 5,730 years. And then we need to know the amount of carbon-14 at the time the organism died. Well, That's the problem. Nobody was there for that. So we don't know how much carbon-14 there was to start. This is unknown, but it is assumed. So let me give you an example. The current amount that we have right now of carbon-14 is 1 part per trillion. It's a very small amount. But if we get a sample of carbon-14 that has 1 part per 4 trillion, so now it's been cut into fourths, we know that organism has gone through 2 half-lives, right? We started with 1 part per trillion, then we went through 1 half-life and we've got 1 part per 2 trillion, and then we went through another half-life and we've got 1 part per 4 trillion since its death. We can therefore derive the organism died 11,460 years ago. Because we know the half-life is 5,730 years, we know it went through 2 half-lives, and that's how we get the date. Does that, people follow that okay? All right, perfect. With current mass spectrometer technology, carbon-14 dating is useful to around 80,000 years. 14 half-lives worth of carbon-14. And I want you to remember this, if there's nothing else you take away from this whole talk, the next time someone throws out, we know the Earth is billions of years old because of carbon-14 dating, I want you to know this one fact. It's only useful to about 80,000 years. Carbon dating does not in any way, shape, or form prove that the Earth or that the universe is billions of years old. It is useless after about 80,000 years. Mass spectrometers cannot detect carbon-14 at that small of a level. So if there's one take-home, the answer is no, it's not. Carbon-14 doesn't prove jack in terms of the age of the Earth. So, sorry. So it simply can't do that. It is only useful for relatively young organisms. So, the assumption of carbon-14, the critical assumption here is that that ratio of carbon-14 to carbon-12, the 1 part per trillion that we see today, we are assuming that what we see today is exactly the same as it is in the past. Well, Dr. William Libby, who actually developed carbon-14 dating, he calculated at the time that he developed this that it would take about 30,000 years to reach equilibrium if you started with 0 carbon-14 in the atmosphere. And this was obviously no problem because, as we all know, the Earth is billions of years old. So we've had plenty of time to equilibrate between carbon-14 and nitrogen-14. Therefore, it's always been the same. However, if we actually look, the current production rate of carbon-14 is 18.8 atoms per gram of carbon per minute, and the current decay rate is 16.1 disintegrations per gram of carbon per minute, meaning we're not at steady state, and actually this alone argues for an Earth that's less than 30,000 years old. Now, at the time that he developed it, Dr. Libby just chose to ignore this problem and said, oh, I must have made an error because we know the Earth is billions of years old. Remember for those of you who were here when we talked last week about the Earth's magnetic field, one of the things the magnetic field does is protect us from cosmic radiation. As we talked about last week, the magnetic field is decaying. That decay will change the rate at which we're exposed to cosmic radiation and will therefore change the rate at which nitrogen-14 is turned into carbon-14. So as such, the amount of carbon-14 produced actually would have been less in the past than it is today, as we were more protected from cosmic rays back then. The magnetic field is getting weaker, so we're getting more exposed to cosmic rays now, so the rate of production of carbon-14 is higher now. Well, what does that mean? Well, if we produced less carbon-14 in the past, it would mean that we see less samples of old organisms we study today, and we are assuming that they're older than they are. In other words, if the rate of production was lower in the past, we're actually overdating how old these organisms are. So, scientists are well aware of this problem. They're actually well aware of both. They're well aware that we're not in equilibrium. They're well aware of what I talked about as far as the magnetic field. And so they've come up with a solution. And this is called dendrochronology. And I was so excited to be able to include trees. So, the way this works is that scientists take tree rings and they take the ratio of carbon-14 to carbon-12 in those rings. And we know, because we're all taught as kids, that every ring equals 1 year of growth. And so we can use that to learn about the composition or the ratio of carbon-14 to carbon-12 at that time, and then we use that information to draw what they call a calibration curve, a correction factor, if you will. So we look at the tree rings, we compare the ratios there, and we use that to give a curve. So if we find a ring that's 1,000 years old, we compare that carbon-14, carbon-12 composition, and then use that to date things that are around 1,000 years old. We use that same calibration curve. So it's an interesting idea. The problem is, as we talked about last week, the oldest tree is thought to be about 4,500 years old. That's not even one half-life of carbon. So these curves are drawn much, much longer than that. So they get this much, so you're taking a big graph this big, they get this much data and just project it out about this far. So no single tree is old enough to properly calibrate. So multiple trees with overlapping time frames are actually used. Now there's lots of assumption about these ages of trees, and we know that trees grow differently in different areas, and they'll show very, very different ring patterns. And some rings are extremely small as 40 rings per centimeter. Very, very hard to know that you're getting an accurate ring. And also some rings, as we also know, are just absent due to very poor growth that year. So ultimately, dendrochronology just is not that reliable of a correction to these curves. So what about the flood? Well, Noah's flood actually would have greatly thrown off both dendrochronology and carbon-14 levels. See, no tree survived the flood. And the flood would have taken massive amounts of carbon that was there in the quote-unquote pool of carbon and turned it into limestone, coal, oil shale, and that would throw off all of the calibration. Additionally, post-flood volcanoes would have thrown massive amounts of primordial CO2, meaning carbon that was way deep buried in the earth and wasn't really exposed to the flood, and then a volcano erupts and throws that primordial carbon dioxide with a different ratio into the air. And this CO2 would have much lower concentration of carbon-14 because it hasn't been exposed to the air to equilibrate. So it's the old stuff that has very little carbon-14. Suddenly it's massively spewed into the air and throws off the ratios. And so it again makes an animal that took that up look much older than it was, because that animal took up a very tiny amount of carbon-14 because that's all there was. And so we say, oh, that animal's really old. Well, he's not. He just happened to inhale volcano ash from an older form of carbon. So the most fascinating to me, because I'm a dork, part of this whole discussion was the research from the RATE team. And the RATE team stands for Radioisotopes and the Age of the Earth. And this group was formed in 1997 and funded by the ICR, which is the Institute for Creation Research, the Creation Research Society, and Answers in Genesis. And they said, okay guys, your goal is to study the age of the Earth. And these were all PhDs. They had 2 geologists, a geophysicist, 3 physicists, and a meteorologist. And they put this group together and they said, here's some money, go at it. And they conducted their experiments over an 8-year period, and their data has become critical to understanding creation research. And so when you hear the term creation science, this is pretty much the definition of creation science, is these guys. They have done some great work on challenging the assumptions of secular origins. So let's look at a couple examples of things the RATE team has produced. Secular scientists, as we all know, tell us that coal is millions of years old, depending on where it's found, somewhere between 30 million and 300 million years old. Well, the RATE scientists said, great, we're going to collect 10 samples from various coal fields through the various spectrum of ages, if you will. And they went to the U.S. Department of Energy Coal Sample Bank, which is maintained at Penn State University. It is sort of the gold standard if you're a coal nerd. That's where you go. And so they got 10 different samples, and they put each of these samples through a carbon-14 analyzer 4 times, and then they averaged the result. Now, the most important thing here, keep in mind, like what I told you earlier, the half-life of carbon-14 is 5,730 years. And after about 80,000 to 100,000 years old, the amount of carbon-14 is too small to detect. These samples are all known to be millions and millions and millions and millions of years old, so what did we find? Every piece of coal had detectable carbon-14. And on average, that coal was dating to about 45,000 years old, which is a far cry from millions of years. So you can see here, these are their various samples that they took from the various places around the country. These are the conventional ages of said coal, and these are the ratios of carbon-14 to carbon-12. The fact that they could detect any in here tells you that by the secularists' own definition, this coal cannot be millions of years old. They did the same thing with diamonds. And because diamonds, we know, are even older than coal. And what diamonds are pure carbon. So that it's crystallized carbon. And so it's all carbon. They took 12 diamonds, and they all contained carbon-14 at an average percent modern carbon of 0.09. And this gives the diamonds an age of around 55,000 years old. So these diamonds that are supposed to be millions of years old, even older than coal, are dating into the tens of thousands. So let's turn, before I do, any questions on carbon-14 before I turn to other, yes ma'am? I'm good. How do I what? Oh, sane. Oh, that's nice. I don't know. That's how I do it. That's how I keep saying. I just drink. So no, that's a fair point. Yes, sir. Mm-hmm. Fair question. I didn't get into that. My short answer is I don't think so. For example, when they date things like the Shroud of Turin and say, "Oh, we know the Shroud didn't," we know it because carbon-14. There were several problems with the Shroud dating. One is they were probably dating the pollen on the Shroud rather than the Shroud itself. Whether or not carbon-14 is useful at all, I think, is up for debate. And so your point is well taken. I mean, for the things that we're all told that we're dating for carbon-14, is it really useful? My personal bias is no, based on everything I've said. The Shroud has kind of had its own topics on carbon-14, but yeah. Mm-hmm. 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 Yeah, and I don't think they have any interest in trying because it would undermine their position, basically. So we all know carbon-14 is completely accurate, so why would we bother? And that's why the data from the rate team is so interesting, is because these guys are doing stuff that no secular scientist is willing to do. Nobody wants to challenge the basic assumptions. It's basically like saying, hey, we don't think gravity exists. Well, come on, who's going to do an experiment to prove that? Well, that's essentially what these rate team people are doing. So. All right, so turning to other radioisotopes. So we've talked about dating organic material, things that are made of carbon, plants, animals, humans. And carbon-14 is very, quote-unquote, useful for dating that, things that are carbon-based. However, rocks aren't living and aren't made of carbon. And as we talked about, carbon dating is only useful for things that are about 80,000 years old. So how do the scientists date the Earth to billions of years old? Well, what they use other dating methods. Things like potassium, argon, rubidium, strontium, and lead dating. And I'm not going to talk about each one of these individually, but we'll go over at least a couple of them. So let me back up first and talk about rock formation. We already discussed sedimentary rock, which contains most of the world's fossils. These are sandstone, shale. This is the rock that's laid down slowly as debris precipitates out of water. Well, there's a different type of rock called igneous, which forms when hot molten material, basically volcanic eruptions, as it cools and solidifies. And this includes all of our countertops, granite and basalt. In the molten state, when this is volcanic, when the volcano is eruption and it's in the molten state, the gaseous daughter isotopes. Remember, daughter isotopes are things like nitrogen-14. You turn carbon-14 into nitrogen-14. Nitrogen is a gas. Some of the things that we're going to talk about also have gaseous isotopes, and so when it's in liquid form, it can easily diffuse out to the atmosphere. But when the rock solidifies, when it comes together, the only source for daughter isotopes are the parent isotopes. So there's no carbon-14 in rocks, but just using the example, if there was, you would give off all the nitrogen-14 as the rock is cooling and still liquid, and then finally it forms into a rock. Now you've got carbon-14, but the only source for nitrogen-14 is that carbon-14, because the nitrogen was given off. So using these same half-lives, we can then measure the daughter isotope relative to the parent isotope and derive an age for the rock based on that known half-life. And the initial one that was done is this one right here, potassium-40 turning into argon-40 with a half-life of 1.3 billion years. And then these are other ones that are used there. So potassium-argon dating. So potassium, much like carbon, exists in three forms. Potassium-39, meaning it's a mix of protons and neutrons that adds up to 39, which is 93% of the potassium out there. Potassium-40, which is a very small percentage, 1/100th basically of a percent is potassium-40, and then potassium-41. Well, potassium-40 is radioactive, and it can decay in two ways. The majority is the beta decay, that's the giving off of the electron. That's how 90% of it decays and turns into calcium. But then there's also electron capture. We take back an electron, and that's 10%, and that turns into argon-40. So we've got potassium-40, which is a rare subset of the potassium out there, but it is radioactive, and 10% of that turns into argon-40 with a half rate of 1.3 billion years. Argon is what's called a noble gas. The nice thing about noble gases is they do not react with anything. They simply dissipate away when it can. Now in liquid form, argon evaporates away very quickly. But once that solid rock is formed, the gas really can't very easily escape. So we can measure the amount of argon in the rock and compare it to potassium-40 in the rock and get a rough assumption of the rock's age. Make sense? So using a single sample of rock, we take our rock sample, we take it to the mass spectrometer, we use the potassium-argon dating. This gives us what's called the model age of the rock. Again, much like my potato example at the beginning, there are a lot of assumptions here. Number one, we know the starting condition of the rock, i.e. there was no argon in that rock when that rock was formed. Number two, we know the amount of parents, the potassium, and the daughters, the argon, has not been altered by anything other than radioactive decay. And number three, we assume that the decay rates have always been with a half-life of 1.3 billion years. And so this technique has been used and has actually become fairly cheap and expedient and easy to do, and it's been used to date numerous rocks and has dated some rocks at the base of the Grand Canyon to about 770 to 870 million years old. And this is how we, quote-unquote, know how old the Grand Canyon is from potassium-argon dating at the base of the Grand Canyon. So let's challenge assumption number one, that there was no daughter, there was no argon in that rock when it was formed. So the RATE team used potassium-argon dating to date a rock that they know was formed from Mount St. Helens in 1986. I've told you many times, Mount St. Helens is one of the most important things for creation research out there. And that rock that was formed in 1986, you know how old it dated? Somewhere between 500,000 and 2.8 million years old. Similarly, there was a volcano in New Zealand, and I'm not sure I can pronounce this. I'll just go with that. We'll just say it's that mountain there. And the rocks there were known to come from eruptions in 1949, 1954, and 1975. And so they sampled these, and they did the same thing. They did with dating of potassium-argon, and you got somewhere between 250,000 years old and 3.5 million years old. Rocks that were maybe 50 years old. So this showed two things. First, the assumption that there is zero daughter present at origin was wrong. Second, it just calls into question all potassium-argon dating. So secularists know this. Much like dendrochronology, they developed something called isochrons. So isochrons are a different form of radioisotope dating, something using rubidium-strontium dating. And this is another dating method similar to potassium argon. The parent is the rubidium, the daughter is the strontium, and they use something called isochrons. So let me try to explain. This is probably the most complex part, so stay with me. Different components. So rocks are made of different components. And different subcomponents of that rock, if you will take up radioactive elements differently. In other words, certain parts of the rock, like the quartz part, will have more or less rubidium, that's the parent, than others like biotite. So this part of the rock has more parent, this part of the rock has a little less. Now the rock as a whole has a certain amount, but we're going to look at the subparts of the rock. And what they do is they test each tiny subpart for its presence of both rubidium and strontium, both the parent and the daughter. Complete side note, don't get confused by this, but they actually do something a little different. They don't actually measure the rubidium and the strontium. They measure the rubidium relative to strontium-86, which is a stable component, and they measure the strontium-87 relative to the strontium-86. I say that for completeness. Don't worry about that. It's very technical. But basically, they measure the rubidium and the strontium in the various subcomponents of the rock. Then they graph it, and they draw a line through them. And if the line isn't straight, if it doesn't straight, they say, okay, the data's corrupted, therefore that we know there was either an influx or an outflux of parents or daughters, something happened here, and this is not useful, so they throw out that data. So that answers the assumption number 2, which was lack of forces other than radioactive decay. So this is their attempt to answer the second problem. And what they do is they take this line, they can draw it backwards to give the age of the rock, even if daughter was present. So this conquers assumption number 1. Even if daughter was present, we can tell from these isochron graphs how old the daughter is. I'm going to try to show this. These dark circles represent the various amounts of rubidium and strontium in different subcomponents of the rock. So we know that, say, the quartz component is here, the biotite component is here, the something else I can't think of is here, and you draw this line, and this is your theoretical line of where you think the original starting point was. And so you move at this same slope this way, this way, this way. This line is theoretical. This line is measured based on the subtypes. This line is theoretical. Where these points meet is the age of the rock. This is isochron dating. And so you can see here they don't meet all the way down here with 0 daughter. They meet right here with some amount of daughter. So it takes care of that first assumption. So this was their gold standard. Their answer to everything was isochrons. So is it the gold standard? Because isochrons take away 2 controversial assumptions, that there were no daughter present at the time of creation of the rock, and that nothing came in or out of the system. These are now considered highly reliable and the gold standard for dating. And basically, what they've really shown is that potassium argon dating, which you'll still hear about today, is inaccurate, and this has replaced it. But the costs of doing this are much higher than potassium argon, as obviously it's a very complex procedure. So you'll still see a lot of dates quoted using potassium argon dates, even though ultimately they know it's garbage. One thing I want you to keep in mind, and I try to emphasize this wherever I can in all of these talks, is that before isochron dating came out, all the scientists knew the Cardenas Belt. Remember, that's what I told you was the base of the Grand Canyon. They knew that the Grand Canyon was 770 to 870 million years old. Once they did isochron dating, they knew it was 715 million years old. But then they came up with rubidium-strontium dating for isochron dating, and now they know that it's 1.1 billion years old. But you were just an ignorant religious person if you didn't believe their dates every single time, even though their dates don't agree at all. And once again, the Bible's been very consistent about how old this stuff is, and the date don't change. But just remember that every time somebody tells you something is science and we know it, that this science is constantly changing. The Bible does not change. The Bible tells us the earth was created in 6 days. That has never changed from when it was written. So let's look at some inconsistencies in isochron dating. Remember those new rocks from Mount St. Helens and from New Zealand that dated about 250,000 to 3.5 million years old? Well, how did the isochrons perform? So the rubidium strontium called them 133 million years old. Samarium and neodymium was 200 million years old, and lead dating said 3.9 billion years old. Keep in mind these rocks were about 50 years old. These same samples from the Cardenas Belt, again, the oldest part of the Grand Canyon, they were compared with the Western Canyon part, the newest part. So we know from science that a certain part of the Grand Canyon is much older than another part. So the oldest part, using the same isochron dating, dated to 1.1 billion years old. The newest part dated to 1.14, which doesn't make sense. Here is a table from this same book from the rate team showing the same thing. And I'm not going to walk you through each one of these, but suffice it to say, take any of your example. This is the volcano from New Zealand. So what did potassium argon dating it? Remember, like we said, somewhere between 250,000 and 3.5 million years old. Rubidium strontium 133, samarium neodymium 197, lead 3.9 billion. Okay? And you can see these examples as you walk down all of the different samples that the rate team tested, the vast discrepancies between the dates. Yet every single scientist will tell you they know that these rocks are that age. So, finally, covering some other studies that the rate team did. Zircons. Granite, again, what's in our countertop, or a lot of our countertops, is made from quartz, feldspar, and biotite. Biotite is 1 to 5% of most granite and actually contains crystals of what's called zirconium sulfate. And these are incredibly small. Actually, when you find zirconium sulfate in larger sizes, we buy them for our wives. So zircons, these zircons that are there, these little tiny crystals that are there, they can and do incorporate uranium and thorium into their structures. And remember from the very beginning of the talk, uranium and thorium are highly radioactive materials. And as they decay, their alpha particles, those 2 protons, 2 neutrons, eventually they combine with 2 electrons and become helium. Helium is 2 protons, 2 neutrons, 2 electrons. Helium, we all know because we've seen it in balloons, floats away very easily. So you take the alpha decay, which is most of the helium atom, we add it with 2 electrons, it becomes helium, and it goes away. So, in 1974, there was some deep drilling in New Mexico, and they extracted granite at very deep depths, 2.5 miles down. And they said, great, let's date this. Let's see how old it is. And they did the lead dating, and they said, you know what? We know it's 1.5 billion years old. Perfect. Okay. So during that time, that decay that formed helium, all of that helium should be long gone. After about 100,000 years, that helium that forms, that was produced by the uranium, should have diffused away a long time ago. However, samples at 1,000 meters deep contained 58% of the total helium generated by nuclear decay. And even all the way down at 2,900 meters, the sample still contains 17% of their helium. This is the oldest sample. And at greater depth, the temperatures are higher, so there should be more diffusion away. So in other words, when they dig really deep, that's where the gas is the hottest, so it should easily go away, yet they still found 17% of the expected helium in there. And this created a huge problem for evolutionists, and one they still haven't solved. Now, the rate team decided to pour some salt in the wound, and they did a couple other studies. So they studied the diffusion of helium out of both the zircon crystals and the surrounding biotite. So these zircon crystals exist in biotite, and the theory from the secularists was, well, we think the biotite actually holds in the helium. Yeah, it can leave the zircon, but the biotite holds it on. And this was to disprove that theory. And then they mapped the rate of diffusion of helium out of these two structures at various temperatures. So they studied the zircon and the biotite, and they said, okay, how long does it really take for helium to get out of there? And then they used software to predict the diffusion rates necessary for these crystals to hold on to their concentration of helium that they actually found. So what they did is they said, okay, we've got this information for how long it takes helium to diffuse out. Now, let's produce two models. Let's say this sample is 1.5 billion years old. How slowly does helium have to diffuse out in order for this amount of helium to still be present? And then they did a second model and said, okay, let's say the sample is only 6,000 years old. How slowly does helium have to diffuse out for there still to be an example? And what they found was the 6,000-year model lined up exactly with the diffusion rates that they see. The 1.5 billion year model, it was only off by a factor of 100,000. So these black dots here, this is what they actually measured the diffusion rates of helium to be out of the model, or out of the sample. Using the model of 1.9 billion years old, this is what the rates would have to be for that amount of helium to be there. Using the 6,000 year model, this is what the rates would have to be, and gosh, those line up really, really well. So one final note on helium. Helium actually diffuses into the atmosphere at a known rate, with only some of it escaping into outer space. And the amount of helium in our atmosphere is not nearly enough to account for an Earth being 4.5 billion years old. In fact, if you start at 0 helium, we would reach today's helium in 1.8 million years. This is going back to what we talked about last week, the uniformitarianism model. And in reality, Noah's flood would have released massive amounts of helium into the air, explaining how we only got there in 6,000 years. Finally, radio halos. As radioactive decays in these zircon crystals, these alpha particles, remember, they're very damaging. Radiation is very damaging. They actually, as they diffuse out, they create damage to the area, and they do so in a very unique pattern that looks like tree rings. So actually these alpha particles that are dangerous, they go out in all directions. And so if I go in all directions and I keep turning from a central point, I'll create a circle. So each step in decay from uranium-238, that first thing that I showed at the beginning, all the way down to lead-206, produces an alpha particle with different energies. And then based on the energy, here's the center. So a low energy moves to here, a high energy makes it all the way out here, and they create these rings. So it migrates a certain distance, and it is eventually viewed as a circle when you slice it through the layers. So a standard uranium radio halo will have 8 rings for each of the 8 alpha particles produced as uranium decays to lead. Well, there's 3 steps in this process that occur extremely quickly. The polonium steps have a half-life of 138 days, some fraction of a second, and 3.1 minutes. But what puzzles scientists is we often find radio halos with just these 3. We don't have any parent, we have just these 3. How is that possible? Where is the parent uranium in its rings? And remember that above certain temperatures, rocks will actually remelt and the halos themselves will be destroyed. So the RATE team isolated numerous samples and prepared slides of rocks thought to be very, very old, that they called the Precambrian or pre-flood rocks, moderately old, and then relatively young. And they actually discovered the oldest rocks had an average of 1.5 of these halos, the medium ones had 8.3, and the newest ones had barely any. Well, the oldest rocks likely lost most of their radio halos during the flood due to elevated temperatures and pressures. The newest ones haven't had enough time to be created. So the first conclusion is that most polonium halos, radio halos, were not formed at creation, as we have fewer of those than we do from the flood era rocks. The second conclusion is the flood may have actually caused accelerated rates of decay, and this is a very interesting theory from the RATE team. They have an idea that maybe radioactive rates of decay have been different over time, and their final conclusion is that radioisotopes do not exist in a closed system. So what do I mean by that? It turns out that many of the polonium radio halos were near uranium halos, and the theory is that while the rocks were cooling, radon, which is a gas in that step, was pushed along the heated fluid and redeposited in areas that have high sulfur content that allows these polonium halos to form. And so if this is all true, and I know this is getting really technical and I'm talking fast and I'm running out of time, but if this would true, this would seriously challenge the theories of a closed system so important to radioisotope dating. This is exactly your question. What we're talking about is there a system that's constant? The answer based on this data is probably not. So the final thought, one other way that radio halos point to a young Earth is the fact that they even exist. Remember that at high temperatures, things like volcanic eruptions, tectonic earthquake activity, they would destroy these halos. And how many of those activities would have happened over 4.5 billion years old? All kinds of them. We shouldn't actually see these radio halos. Finally, the accelerated nuclear decay. Again, the rate theory has some interesting theories that accelerated nuclear decay may explain some of the problems we see with radioisotope dating. Their theory was during creation week and then again during the flood, nuclear decay rates were much faster than what we see today, i.e. the half-life of these isotopes was much shorter than what we see today. Much of their work is still theoretical, but it goes a long way to explain many of the things we've already discussed. So in conclusion, radioisotopes are a very interesting concept, but they're full of assumptions, flaws, and inconsistencies. And various methods result in far different rates for the same rock. They can't all be correct. So if potassium argon says one thing and rubidium strontium says another, one of them is right or both of them are wrong. And thanks to the rate team, we see that much in radioisotope dating actually points to a young Earth and recent creation. Now, there's many unanswered questions, and I'd remind you of what I said at the very beginning. Radioisotope dating is still a formidable challenge to young Earth theories. However, the more we learn about it, the less troubling it is as we seem to find more and more flaws. So, did we get all of that? That's I'm a big Nicolas Cage fan. So, sorry, a little bit overwhelming. I apologize. It gets simpler from here. What questions, if any, can I answer about any of that? Okay. Around the 1700s. So, yeah, the geologists were the first ones to say that, and then they kind of got together with the geologists said, well, the rocks are this old, and they kind of got together with paleontologists said, well, if the rocks are that old, the fossils must be this old. So they started kind of buying into it. And then radioisotope dating came around in the mid-40s, mid-50s, somewhere around that time. So the original theories were the Earth was probably around 300 million years old until the last century, and then they've gone from 300 million to billions, basically. Mm-hmm. That's a good question. I mean, that's fair. It is a little hard to say the ones where you're looking at 1.8 billion years old that they can actually measure those half-lives, but most of what I've read, and I think it's true, is that the technology probably is there to do that. I mean, you have so many decays. I mean, remember, atoms are so small, so it doesn't take very much of a sample to really get an idea. So those rates are probably pretty close to correct. But totally fair question. Good. Yes, sir. Mm-hmm. Yes. Well, it goes back to, is carbon-14 dating reliable at all? And so I think the short answer is no. The other thing is all the other things we talked about during the flood, you would have changed the amount of composition in carbon in the Earth, and so we're probably overdating. Even if carbon-14 dating is accurate, we're overdating because of some of those other things that we talked about. So it would still date to around 6,000 most likely. Yes. That's okay. Somebody mentioned that, I think. Yes, somebody said they saw that on the news. And yeah. Yeah. Yeah, they're always impressed. Huh? Yeah. Yeah. Sure. Of course it is. They'll, I mean, our grandkids will be told it's 100 billion years old. I mean, it's just gonna, and then we were all rubes and for thinking it was 14. So, again, the Bible's been very consistent. Good. Yes, sir. Yeah. I don't know. I don't know the answer to that. You always have questions I don't know the answer to. No, it's a good question. I don't know. I do think they probably are. I think we have to sort of take it that they probably have calibrated them correctly. Even if they ultimately, my point on radioisotope dating is I just think the whole field is garbage. I mean, not being overly obnoxious about it, but I see too many flaws, too many inconsistencies to be excited. And could that be a reason that it is? Yes. But I think it has more to do with the fact we just haven't reached steady state. And that we're studying things in such a short period of time. Even if the Earth is 6,000 years old, we're still looking at, we're doing these measurements over 20 years. Well, we don't know what the Earth was like at creation or during the flood or anything like that. So that's a good question on calibration. I don't know. So. All right, guys. Well, hey, I appreciate everybody coming. Next week, we're going to talk about paleontology for the first half of the class, and then after that, we start on to Noah's flood. So, and I'll be around for a little while if anybody has any other questions, and thanks, everybody, for coming back.